All right, let's talk about center of masses and inertias, rotational inertias of weird things like this thing. No idea what that is. So let's talk first about this system of objects that aren't necessarily connected, but we still want to know the center of mass of these objects. So we can use this first equation to solve for that one because we're not dealing with I. So and what the differentiation between whether or not you're solving for I and whether or not you're solving for just a center of mass would be if you're given a pivot point, which is normally labeled P. So now that we know that that's what we're doing radius of the center of mass. Radius of the center of mass is equal to the sum of all the masses times the radii from a certain given 0, 0 that we get the liberty to set, divided by all the sum of the masses. So, and this one also abides by you have to do x's and y's separately. You just have to. So now let's do this. So we want to solve for radius of the center of mass. We need to set ourselves a 0 point. So I like setting, because we're given a plane here, I like setting the bottom left as 0, 0. So this is our 0, 0, which means that any numbers we get are going to be positive, up or right of this 0, 0 point, and will allow us to set our center of mass. And then before we do anything too, I'm going to also take a guess at where I think the center of mass will be. Well, we have 4 here, 2 here, 2 here. If we look at it quadrantly, we have a heavy mass here, uh, a lighter mass. Like if we look at it from top and bottom, we have way more on the bottom. We have 6 down at the bottom and 2 at the top. So it's probably going to be more towards the bottom. And then we have more towards this left side than this right side. So, but it's kind of also centered out because we also have one in the middle, but we have more mass over here. So we're going to say it's probably going to be somewhere in this area here. That would be my guess. So now we have to look for the radius of our center of mass. And now that we have a guess, if we get a weird number for this and then it doesn't fit in there, we know we did something wrong somewhere. So radius of the center of mass is equal to the sum of the masses times their radii from our 0, 0 point divided by the sum of the masses. So let's go RCM in the x direction. So is equal to the sum of the masses from the radii from 0, 0 just in the x direction. So we have 4 is 1 to the right of our 0, 0. So 4 plus, so 4 times 1 would be 4. Plus from this second mass, it would be 2 over times 2, so 4. And then this final one would be 4 over times 2, so 8. Divided by the sum of all the masses, 2 plus 2 plus 4 is 8. So that would mean that this entire thing, RCM in the x direction, is equal to 4 plus 4 plus 8 divided by 8. So that would be 16, so 2. So that would mean it would be somewhere along this center line. Hey, that's a pretty good start so far. So that would mean it would be 2 in the x direction. Now let's do it RCM in the y. RCM in the y direction is equal to our equation. So now we'll do the same exact thing, but look at how far they are from the y. This one is 1 up, so 4 times 1. This one is 3 up times 2 is 6. This one is 1 up plus 2 is 4, and then all divided by 8 again. So RCM in the y is equal to 4 times 6 plus 2, which is 12 divided by 8, so 1.5. And it's also 1 meter by 1 meter. I scaled it. So we have 2 meters and then 1.5 meters, meaning our center of mass is at 2, 1.5. I swear to you, I didn't do this beforehand. That was a random guess. So that means that there is our center of mass, because it's going to be that much differing from our equilibrium point. So therefore, that is our center of mass mass of this system. Cool. Nice voice crack. Thanks. That is going to be the center of mass of our system. Now let's solve for rotational inertia, given a weird system as well. So we have our pivot point here, and then a mass 2 kilograms here, a mass 2 kilograms here, a mass 3 kilograms here. So what determines our I this time is this R is dependent on how far things are from a pivot point, not a random equilibrium point we set. It's only from this pivot point. And one thing that's nice about I, though, is that R has to be directly to. There's no separate X's and Y's. R has to be directly to the pivot point, meaning that this distance, oh, I'm going to use a different color. This distance here is what R is for this mass. This distance here is what R equals for this mass. This distance here is what R equals for that mass. And then we just sum all those up. So that means we have I is equal to, oh, I'm using a different color. I is equal to the sum of the masses times the radii squared. I is equal to mass times radii squared of the first mass. So mass times radii of the first square. So 2 times 2 squared, because it's 2 meters from that center mass. So that actually gives us that value. Plus this next one. Let's do the 3. So the 3 is 4 to the right and 3 up, which if you'll recognize that is a Pythagorean triple triangle, meaning that slanted value there is 5. So we're going to have 3, the mass, times 5, the radius squared, plus the same thing because it's just 2, 2, and 3 again. So it's a Pythagorean triple triangle again, except this time we're going to have 2 times 5 squared, all in parentheses. So I is equal to all of that. So let us put that one in now. 2 squared plus 3 5 squared plus 2 5 squared is equal to 133, which means our moment of inertia, if I grab the right pen, is 133 kilogram meters. I forget the unit for it. How could I forget the units? The unit for moments of inertia is, what is it? Kilogram meters squared. So I was close. Not meters. Meters. I just threw my pen. Meters squared. There we go. That is our moments of inertia. There we go. So now that we have that, we have finished center of mass.